For our project, we did the Balmer series lab. And this lab investigates the properties of the Balmer series, which is a series of spectral lines emitted by the hydrogen atom. So for the setup for this lab, it requires a Pascal optical bench. And on this optical bench, we set up a diffraction grating that has 1,000 lines for every millimeter. And we set this up at position 30. And a quick tip about this is that it might need pieces of paper right here to help balance it so that it's completely straight. And then at position 0, 30 centimeters away, we have a meter stick right here, and we need to make sure to center it at 50 centimeters on this stick. And then we have the high voltage power source, and while this thing is on, you need to absolutely make sure not to touch it because it can be very, very harmful. And what we put into this are the discharge tubes, and first we have mercury for calibration purposes, and then we have the hydrogen discharge tube.
So this is the mercury gas discharge tube. We will be using this to calibrate the diffraction grating. You plug this in by pushing bottom plug in. And once it's fully plugged in, it's gonna stay up front, straight up. We're gonna turn our light off to see the discharge. We will look through the left side and the right side of it to increase our data points accuracy. So I see horizontal lines through this.
So now in this part, we're going to do the Balmer series using the hydrogen gas discharge tube. This gas discharge tube will be placed the same way as the mercury one. However, you have to be careful to only turn it on for 3 seconds at a time so that it won't burn up. Now we're going to go turn off the lights and then get ready to take some data. So in the same way as for the mercury one, a light's used to illuminate the meter stick so it can be read. When I'm ready to start reading it, I will tell him to turn it on so that he knows that I'm ready and we can keep it on for the shortest amount of time possible. So when I'm ready to start reading it, I'll let him know and record it in that 3-second period. So I'm ready?
1, 2, 3.
So when I was looking through there, I saw 4 lines, a red one, blue-green colored one, and then 2 violets. Those will be recorded for both the left side and the right side in the Excel document.
For the results, we were able to accurately find Rydberg's constant with very little % error. First, we needed to find a measurement for the distance between slits in the diffraction grating. After calibrating it with a mercury lamp and performing trigonometric calculations with the diffraction grating formula d sine theta equals lambda, we found that the distance between slits is approximately 1.0047 times 10 to the negative 6 meters. So for each of the colors in the mercury spectrum, we calculated a value of D and then averaged them together to find the average value of the distance between slits in the diffraction grating. So we use this measured values of about 1.0047 micrometers as the value of D for the hydrogen lamp calculations. Using trigonometry and the formula for the behavior of light waves through a diffraction grating, or D sine theta equals lambda, we found a value of Rydberg's constant for each discrete spectra created by the hydrogen light. For the calculated wavelength of deep violet light right here, we got a value of little over 11 million for Rydberg's constant, which is just 0.39% different from the known Rydberg's constant. And then for the other 3 colors, we got values very close to the first one, a little bit below and above 11 million with very similar % differences. They're very low. And With this low error, we are confident in our experimental results and our measurement of the Rydberg's constant, which concludes the Balmer series experiment.
For the conclusion, the hydrogen atoms in the discharge lamp emit a series of lines in the visible light region of the spectrum, called a Balmer series. This series is called because the equation that is used to describe the wavelength of this line was developed by Swiss teacher Johann Balmer. As you can see on the picture on the right, and the equation is 1 over lambda is equal to r times 1 over 2 squared minus 1 over n squared, which n stands for the principal quantum number. The calculated Rydberg constant was very close to the expected value for our experiment. This confirms that the setup used is able to accurately measure spectral lines in the Balmer series. The Balmer series equation does not use the lowest energy as n equals 1 instead of using n equals 2. This is because any drop in n equals 1 releases a photon in the UV spectrum and is not visible to the human eye.
Some ideas for future experiments are testing different spectral series. So each of the spectral lines releases different amounts of energy based on the number of orbital transitions from higher energy to lower energy orbits. The Balmer series is only one way to describe the spectral series for hydrogen. In future experiments, different series outside of the visible spectrum could be tested, such as the Lyman series, which is in the UV spectrum, the Pachon series, the Burkitt series, and the Pafun series, which are all in the infrared spectrums. The Lyman series releases the biggest energy as orbital differences are the biggest, and each of the subsequent series releases lower energies. We are only able to do experiments on the Balmer series since those spectral lines were in the visible region. But with the proper equipment and preparation, we could test other spectrum series at either the UV region or the infrared region.
So for our sources of error, we have some issues with the setup. So our setup only allows for the eyes, the human eyes, to be used to determine the position of the spectral lines. So since our eyes are not extremely precise, we can't get the exact measurement of the spectral lines down to a very, very small value. A solution to this could be using a setup that includes movable light sensors that can record the exact location of each spectral line. Another source of error for this experiment is that a slight movement of the apparatus during the experiment could result in an inaccuracy in the results. So therefore, we must be very cautious while doing the experiment. So we cannot be completely sure that no slight movement occurred.
So in this project, we learned a lot more about the Balmer series and got to see it with our eyes. And we also, in doing research about it, we learned about different series that are outside of the visible range that the hydrogen atom emits.
This lab experiment helped me understand the different orbitals and the behavior of the hydrogen atom, especially how the energy changes as it goes from one level to another.
Thank you for watching our project. I hope you guys learned at least something about Balmer series and take something home with it.